CN Tower in Toronto is the tallest freestanding structure in the world. So what is it that today lets us build buildings so tall, when just 200 years ago, the tallest buildings were the Gothic cathedrals, buildings that would be dwarfed by this amazing structure? That is the question we're going to look at in this programme. So far in this series, we've seen that the shape of a structure, or a structural member, is more important than the quantity of material. Equally important is the area over which the shape acts. Here's what I mean. If you increase the area over which something acts, you can reduce its intensity. That's why we wear snowshoes. The opposite, of course, is true too. If you reduce the area over which a force is acting, then you increase its intensity. That was the trouble with stiletto heels. You see, when secretaries go out on roofs at lunchtime, they could each be exerting something like 1/4 of a ton at the tip of their heels, even with a fairly light damsel. If she happened to rock back on both heels at once, there would be enough force to punch a hole through the roof. This is all because of an increase in the intensity of the force, the person's weight in this case, due to the small area it is acting over. This intensity is called stress by architects and engineers. Well, what does this have to do with buildings? Let's look at a typical early wall, such as a dry stone wall. That's the type that uses no mortar. Now, each stone is pushing down on the stone below, so the load is increasing as we approach the bottom of the wall. Now, the only way to stop the stress building up too high is to increase the area over which it acts. Now, that's one of the reasons for having a battered wall. That is to say, one that is sloping because it's wider at the bottom than it is at the top. So the area is increasing as the load is increasing, but the stress remains the same. It's a basic law of nature. It's why the Great Pyramids in Egypt and Mexico are battered, and it's also why mountains are shaped the way they are. Here's another example from nature. These are the Badlands of the southwestern United States. These signs tell the tourists that the unusual shapes are the result of erosion by the wind. But what they don't talk about is the fact that the area erodes the way it does because the grains of sand directly under the rock on the top are under more compressive stress, and that makes them harder to remove. So the wind takes away the grains on the outside, but leaves a conical pillar still standing. In other words, proper control of stress can lead to stability. This is an important lesson to remember. Let's look at this wall again. Which of the stones would we find easiest to remove? One at the top, where the stress is minimal? Or one from the bottom, with the weight of all the other stones pushing down on it? There are, of course, many man-made examples of battered or tapered walls. Think about those medieval movies we've all seen. Castle walls are built the same way. They are battered to be wider at the bottom. So are the walls of dams and buttresses. Now, we don't often build battered walls these days. Modern walls in brick or concrete are quite capable of taking the increased stress at the bottom of the wall without making it wider. But today we add a footing under the wall to do the job just like a snowshoe. So, now let's move on to walls that hold up roofs and the effect that that would have on their design. Well, if you look at the joists, you can see that that wall is holding up the roof, and so is that one. And that's typical of most simple construction, just two walls holding up the roof. And they are called load-bearing walls. Now, the principles in designing them are the same as they are for any wall, but architects and engineers have to design into load-bearing walls an ability to cope with the extra loads imposed on them by the weight of the roof, plus any additional loads, like snow that might build up on that roof. Now, in most construction, the load-bearing walls shouldn't have the large openings in them, like windows and entrances, if it can be avoided. Ideally, they should be in the other walls that are holding up just themselves and can be added later. You may well see that same principle employed in your own house. It really is just common sense. Of Of course, you can have openings in load-bearing walls, but you have to use small beams or lintels over the openings, which of course will cost more. Well, that's okay for walls holding up trusses and beams. They are what we call closed systems. That is to say, their weight is acting directly down. But many of the old roofs on buildings were domes and arches, or sloped and pushed outwards as well as down. What happens when a wall has to contend with that? Well, the trick is to make the wall much thicker. But such a wall doesn't necessarily have to be completely solid. It resists the outward thrust of, say, a domed roof, simply because its weight is spread over a larger area at its base, and it's more difficult to tip it over. We can show that easily. I've got two pieces of scrap wood here representing walls of the same height, but this one gets thicker as you go towards the base. Now, if I push the thin one from the side, it takes a small force only to push it over, whereas it takes a much greater force to tip over the thick one. Now, it's all very well to have thick walls if you don't need large windows in them. But in the more northern parts of Europe, for instance, where there's much less daylight than there is along, say, the shores of the Mediterranean, people needed big windows, especially in those large churches and cathedrals. Now, this presented a problem. It's very difficult for high, thick walls to contend with large openings and still act properly. Oh, you could certainly have windows in the non-load-bearing walls at the ends of a long, thin church, but that wouldn't give enough light inside it. The way medieval builders solved this problem was to build buttresses. They were props to hold up the wall and were placed where the major roof members met the wall. In other words, the buttress made the wall thick in places where it needed to be thick and were often battered as well. You could then use the spaces in between for the openings or windows. Now, in the past, the only way to design walls and even whole buildings was by trial and error. If the wall or the building fell down, it didn't work. Well, there were rules, of course, passed down from father to son, especially through the guilds. I guess they were the equivalent of today's bylaws. No wonder the guilds were very important and secret. Here's an example of an extremely important rule for construction that was found by trial and error. You see, builders had trouble with what are called thrust lines. Now, they are imaginary lines or paths that forces follow in a wall on their way down to the ground. To illustrate that, here's a model of a wall where one of the bricks has been replaced with these layers of foam, and I've divided the whole wall roughly into thirds. Now, if a force is applied compressively at the top, you can see that the whole wall is in compression. If that force gets towards and outside of the middle third, you can see that this part of the wall is no longer in compression. So ideally, that force should be applied within the middle third. Don't ask me why. Undoubtedly, we could prove it with mathematics, but we don't have to. We can see what happens. This path from there down to the ground is called the thrust line. Now, that's an example of a force acting down on the wall. But look at what happens if there's an outward force as well. If the imaginary thrust line gets outside the middle third of the wall might go into tension and want to lean over. If the line goes outside the boundary of the wall, the whole thing falls down. And in fact, in ancient walls, this happened far too often. Now, the simplest way of stopping it is to make the wall thick enough so that the thrust line always stays inside. That, of course, is our battered wall, or buttress. But there is another way to solve the problem of keeping the thrust line within the wall. If you push down more with a big weight, you actually force the thrust line to move in. That increases the compression in the wall and prevents it from falling over. This simple idea actually works. That's why buttresses had turrets, pinnacles or statues on the top. So as well as being part of the overall design, they kept the thrust line from straying outside that magic middle third. As the buildings got higher, or the spans wider, the buttresses had to stick out farther. But if the buttress is so far out that it blocks all the light, what use is it? The solution was to put holes in the buttresses so that light could pass through. This is what we call the flying buttress. The Gothic style of architecture was partly a process of adding material to hold things up, then taking some of it away in places where it wasn't really needed. A very important point to remember is that most structural systems up to a couple of hundred years ago relied solely on compression to hold themselves together. Really, it was, by and large, the weight of pieces on top of one another that kept them from falling down. And this, we have seen, had important consequences for walls, especially stone or brick ones. You couldn't have a load that tried to stretch the wall on one of its sides, which is what happens when a wall is pushed out near the top. Walls could not bend because one of the sides of the wall would be in tension, just like a beam or a blade of grass. But while beams and grass can cope, a wall cannot. It just falls apart, or falls down if it's made in a single piece.
By the way, just an aside here about the mortar people use in their walls between the bricks or stones. Well, contrary to popular belief, mortar is not a glue. No, it just spreads the weight more evenly. It simply transfers the compression of one stone to the stones below. So when they didn't use mortar in the past, it was because the walls were better made, not worse. And yet we often think, oh, poor people, fancy having no mortar to build their walls with. Well, the fact remains, most of the time, they didn't need it. Even to this day, the great stones in the walls at Machu Picchu in Peru are so carefully and smoothly cut that you can't put a razor blade between them. They simply didn't need the mortar.
Machu Picchu is very impressive. But if we want to build large, modern buildings, this technique of using compression only just won't work. The needs of the modern city spelled the end of the load-bearing wall as the primary means of construction. Oh, you can still build using load-bearing walls in smaller buildings, and of course we do. But we immediately find a problem with a building that is built very high. If the walls are load-bearing, then they will be very, very thick at the bottom. These stresses that build up at the bottom are so high that you can't have any large openings in the walls. Well, of course, that's exactly the opposite of what you want in a downtown building. You want the biggest openings at ground level for shops. So we have to find another way. We can find a clue if we go back to our bearing wall system. What if we make walls so short in length that they just become posts in the corners? This can be done, and what we have is a post and beam building. The load-bearing wall is replaced by a post at each end and a great big beam across the top. This is especially good for those buildings where we want the freedom to arrange or rearrange the interior walls any way we want, say for lots of small offices. Then the post and beam system comes into its own. But what is different about the way this system transfers its loads to the ground? Well, remember our diagram from episode 2 of the teeter-totter? When we flip it upside down, we can see that when the load gets nearer to one column, the column has to be made bigger to handle the extra load. Now, this means that in a multi-storey building using post and beam construction, the beams would stay the same size, but the posts should get bigger as you move towards the ground level of the building. Not an economical idea, because the dimensions between the columns change as you change stories. They get narrower, and you end up needing different size windows for each floor. The solution is sometimes to have rows of smaller posts or columns closer together, and that are the same size all the way up the building, which is a more economical form of construction. Now, economy is also a major factor in designing the beams. Let me explain. When you have a row of 3 columns, say, you could have 2 beams from the left-hand post to the middle and the middle to the right. If you put a weight in the middle of one beam, it will bend a certain amount and not affect the other beam at all. But if it was just a single continuous beam over all 3 columns, and you put a weight in the middle of one of the bays, it will still bend down, but the other part will bend up. How does that help us? Well, not yet. But what if we add a weight in the other bay? In the first example, both beams bend the same amount, but with the continuous beam, the downward bending is reduced because of the upward bending that now takes place on both sides. In other words, a more efficient beam, because it needn't be as deep as the separate beams, which saves money. Now, if you continue the beam past the end of the column a bit, you can increase the overall efficiency still further. This is called cantilevering. The load on the cantilever can reduce the bending in the rest of the beam by using the result of upward bending to work for us. A tree is a perfect example of a cantilever in nature. Next time you're on a walk, just look at the branches. Or lampposts, for instance, they're cantilevered too. And this parking garage, the ends are cantilevers. Now, cantilevers play all sorts of roles in buildings today, but here's an interesting example of how their use is governed by climate. You may think when you look at North American cities that all the skyscrapers look the same, but it's not quite true. In the northern parts of the continent, cantilevered beams are used more often than in the south. Why would that be? Well, in the north, with the extremes of climate, the last thing we want to happen is to have our posts or columns unevenly stressed by the changing temperatures. You see, inside the building, there are some columns that go right up the middle, maybe 10 or 20 stories. They are always cosy and warm. If this set of columns stays warm while the outside ones get cold, there can be more than 5 centimetres difference in the total length of the inside and outside columns. That's definitely not good for the building. But if the beams in the building are cantilevered, then the outside columns are effectively pulled inside the building where the climate is controlled. In other words, it's a lot easier to keep them warm too.
The roof over the stands of this football stadium is a great cantilever.
In fact, many stadium roofs use the cantilever to great advantage. Now, I want to show you something important about a cantilever. And once again, I shall turn to my trusty eraser. But now, I'm going to clamp it to the back of this seat and apply a weight to the end of it. And what happens? Well, it scrunches up at the bottom and stretches at the top. In other words, it's tension at the top and compression at the bottom, the opposite to our simple beam between 2 posts. Now, this is important because we have to make sure that we have enough material and of the right sort at the top of a cantilever to handle the tension. And this becomes critical for those amazing large cantilevers, because then we'll use something that's called pre-stressing. Now, I'm going to explain pre-stressing by looking at the clever ways in which the builders of some of the world's greatest dams have looked after a similar problem.
After all, dams are walls, and there is a tremendous sideways thrust on them. So dams are often buttressed, like the walls of a Gothic cathedral. But some dams are very thin. How do they do that? They don't put heavy weights and statues on the top of a dam to keep the thrust line in like the Gothic designers did. But we know that every push can be replaced by an equal and opposite pull. So suppose we drilled holes right through the middle of the dam, down to the bottom, and put long steel rods down them, anchored them to the rock, and put great nuts on the top and tightened them up, so that now they are pulling down. That is pre-stressing. Pre-stressing is an important principle of construction in many modern high-rise buildings. Now, we see concrete everywhere in construction, but ordinary concrete only works when it is compressed. If you try and bend it, in other words, put it into tension, it tends to crumble. That is no good if you're constructing a skyscraper, or any building for that matter. So how can we make this material work under tension and also be pre-stressed? The answer is to put steel rods in the concrete. If it's a concrete beam, the rods go near the bottom, where the tension will be greatest. In any event, the material with steel rods in it is called reinforced concrete. Its importance to modern construction cannot be overemphasized, and it's reinforced concrete that lets us use pre-stressing.
Perhaps the best way to demonstrate pre-stressing is with this pile of books. Now, if I wanted to put this pile on that shelf, say, I could do so by pushing hard on the outside. Mind you, I better push in the right place. Too low down and they pop up in the air. Too high up and they fall on the floor. Now, I've said before that for every push, there can be an equal and opposite pull. So, I could achieve the same result by drilling a hole through the books, tightening up some screws on the end, and there we are. It's a bit rough on the books, I know. But that's exactly what I've done. Not only that, I've now turned this row of books into a beam that could span from there to there and take a push on top. And that's exactly what reinforced concrete is. That's why we have steel inside. But better than that, if I were to tighten it up, then I'm actually pre-stressing the beam. That is, I'm building in a stress to push upwards against any loading that I might put on top. And the neat thing about that is that I've locked in a stress, and so the initial loading of the beam I get for free. In other words, it's simply relieving the stress that I've already built in.
To take this one step further, reinforced concrete and pre-stressing are the keys that let us replace joists and beams with thin slabs in high-rise building construction. Let's return again to our post and beam system, with joists running from beam to beam. In a house, they are usually made of wood. But supposing we were to use reinforced concrete, it would be in the form of a slab spanning between the beams, and you wouldn't need joists at all. The slab would have lots of steel reinforcing along the bottom, running in the direction the joists would have taken. This is called a one-way spanning slab. And just as with beams, if you cantilever the slab, it's more efficient. Now, the interesting thing with slabs is that now for the first time, if you've got lots of reinforcing rods going in one direction, there is nothing to stop you from having a second set running the other way. That's called a two-way spanning slab. You can have 4 beams sharing the load, and the slab could then be thinner. So we've managed in our post and beam building to have eliminated the joists, but we still have a set of beams that the slab sits on. Would there be any advantage if we could get rid of them? Yes, there would. If you put enough reinforcing in a slab along the line of the columns, you don't need the beams. Why is this important? Well, it means that, say, for a 12-storey building, if you can save 20 centimetres on each floor, you could squeeze an extra floor in the same height of building. And we can make the slab even lighter and thinner by removing concrete from where it's not needed. It's called a waffle slab because that's what it looks like. So the thrust today is to make thinner and thinner slabs to create more and more stories in the same height of building. All possible because of reinforced concrete. To end this programme, let's look one more time at the CN Tower. In a way, it can be looked at as a very high wall or column. They were able to build it as tall as it is because of reinforced concrete and pre-stressing. But the tower owes a lot to our Gothic heritage too. After all, those are buttresses at the base of the tower, and those buttresses themselves are battered. Just like the walls that man has been building for thousands of years.
You may have noticed that we're halfway through the series, and so far we've primarily talked about structures whose forces follow straight lines. Well, we should have to do something about that. So in the next programme we're going to talk about arches and their three-dimensional cousins, vaults and domes. That's not supposed to happen.